that's basically where we're going. So up till now, we've talked about Rn and matrices, right? And so we started with the question of system of equations, right? And we studied how to solve a system of equations. We discovered that if you look at matrices, you can understand how to solve systems of equations lots of different ways, right? And we've seen that it's more than that. You can do many things with matrices. They enjoy a certain algebraic structure, which is interesting, right? And we've done a lot of that. But we've also started to bump into this notion of linearity, right? We've seen that we talk about linear transformations that preserve addition, right? And you can pull out scalar multiplication. And I've also pointed out to you that that's something we see in like that pattern of linearity we see throughout math, right? We see it in differentiation, we see it in integration, maybe you see in Laplace transforms, I don't know, limits, sums. It's ubiquitous. I mean, it's all through math, this linearity, right? So then the question then is, you know, is there some sort of deeper truth here that we can sort of ignore the particular details of examples and extract some essential description of what we're looking at? And that's what we're doing today. The idea of a vector space basically is, what is the central core of the structure we're looking at as it concerns linearity? That's what a vector space is we just take away all the unessential details, like it's a column vector, it's a function, it's a matrix, it's a whatever. And we just focus on the essential, you know, what is basic about something having linearity. So in short, what is a vector space? Well, the vector space is a set of something where you can add things and you can do scalar multiplication. All right, that's what a vector space is. The reason we study vector spaces is very simple. If I prove something about vector spaces, right, I've proved that thing, not just about column vectors or functions or matrices or whatever. I've proved it about everything that happens to enjoy this property of linearity. That's why we're doing what we're doing. It's because by taking this abstract approach, we're able to solve an infinity of problems through one simple, elegant argument. So that's why we're doing this abstraction today, this abstraction of what's called a vector space. Now, of course, you can't really appreciate that unless you know what vectors are in Rn and matrices, right? But some of you know what those are.
Yeah.
I think everyone knows.
Are you responding to my what for you, or are you?
Well,
raise your hand if you've been in calculus 3 before. Oh, I see.
So let's get to it. Definition. A vector space, what is it?
A set of something where you can add things and do scalar multiplication.
Very good.
In your perfect words. I'm worshiping Dr. Cook on camera. Look at me. I'm pathetic. My gosh.
He'll sort this out. I need to disown him on camera.
I let Christian speak for himself. So a vector space is a set V, all right, together paired with let's see, a couple mappings. One, some notion of plus, which is a mapping from V cross V back into V again, and scalar, this is called vector addition. And something I use sometimes denote by dot, but you know, now for the most part we're going to be looking at scalar multiplication over the reals. But the truth is, this definition, you could take the reals and replace it with complex, or one of those finite fields we looked at. All right, but I will, as I unfortunately say at times, keep it real today, and we'll just do real vector spaces for the time being. So. Scalar multiplication, you give me a scalar and a vector, I give you back a vector again. So this mapping is called scalar multiplication. All right. Now, more than that, we have to satisfy certain axioms. All right. So here's the axioms: axiom 1, axiom 2, axiom 3. Axiom 4, axiom 5, axiom 6, axiom 7, axiom 8. No. I guess I'll go over here. here. Axiom 9 and axiom 10. All right, I think that's enough. Okay.
Just out of curiosity, so like in the addition thing, where like part of the definition you have v times v, or is that like x means something else?
That's the Cartesian product of v and v.
Oh, okay.
So what I'm saying is, you give me a pair of vectors. This is a function. Addition is a function that takes in a pair of vectors and gives you back a specific vector. So it's a single value.
That's why the
assignment.
arrow goes into a vector.
This is a vector. I mean, v is not a specific vector. V is a set. So first of all, x plus y has to be equal to y plus x for all x and y in v. That's axiom 1. In other words, addition commutes. The other thing is that addition is associative. So x plus y plus z is equal to x plus y plus z for all x, y, z. So English doesn't really help us here, but let me put some parentheses in, right? So in other words, you can add these two and then add that, or you can add the last two first and then add the first one. You get the same thing. Addition is associative. There exists 0 in V. In other words, there exists a so-called additive identity, such that x plus 0 is equal to x for all x in V. All right, so axiom 3 is the existence of an additive identity. And this is kind of tied to axiom 3, but for each x in V, there exists minus x in V, such that what? X plus minus x is equal to that additive identity from axiom 3. So axiom 4 says that there's an additive inverse for each vector in this set. Okay, so these first 4 axioms taken collectively. All right, let me just make a comment here before I go on to the other axioms. These first 4 axioms here collectively tell us that a vector space forms an abelian group with respect to addition. Abelian because of axiom 1. It's a group because this operation of addition is associative. There's an identity, and there's inverses for everything. I also have already stated that the operation of this is actually tied to it too, right? Well, more about that. Anyway, of course, you don't know what an abelian group is because you haven't had group theory yet, but you will, and it's worth commenting on that since we shared this. But a vector space is much more than a abelian group, right? There's extra structure here. The scalar multiplication in particular has lots of nice things. So, scalar multiplication, how do we describe scalar multiplication? 1 times x should be what? Yeah, it should be x. And that's for all x and v. And here I'm writing 1. That's the 1 from the real numbers. Okay, that's the multiplicative identity of the real number 1. Okay. More than that, if I have scalar multiple ab times x, what should that also be equal to? Say what? ABX. It is true that I will use, well, more to the point, Sharon, I mean, I agree, but that's really notation. I mean, AB.x, right? Very soon, we'll use this notation ABX. So like, instead of writing the dot explicitly, we use what's called juxtaposition, just writing it next to each other to indicate the scalar multiplication. I'm not doing that yet because I want to be really clear about where the scalar multiplication is. So, but no, that's not it. It's, how about this, A dot, it shouldn't matter if you do scalar multiplication by B first, and then do scalar multiplication by A, right? So if you have a product of A and B, you can scalar multiply by B first, and then multiply by A, you get the same thing. So that's for all A and B in the reals. and for all x in the vector space. Axiom 7. We have what's called distributivity with respect to the scale multiplication. So, and the vector addition. So a dot x plus y, all right, is what? It's ax plus, we say ay. Yeah. And that has to hold for all a in the reals and for all x and y in the vector space. Run out of axioms. I hope I finished. See here. Oh, and you can also distribute when, yes, Chris?
So is this the dot product, or is this just
No,
a
this
symbol
is-
for multiplication?
No, not dot product. It's the symbol for scalar multiplication. My dot product hopefully looks more like, I know it's going to be hard to see the contrast here, but my dot product, in my notes at least, looks more like this.
Okay.
So, I mean,
That looks like you're like overriding a mistake with a bigger dot or something.
I don't know. I have a specific command in my notes that makes a dot product. It's bigger and bolder and darker. But also for that reason, I stopped writing scalar multiplication as dot, because I don't want you to make you think about dot product. Really, although, you know, honestly speaking, there shouldn't be any confusion for most cases, because a dot product is something we take between vectors, right? Scalar multiplication is on the one side you've got a number, on the other side you got a vector. So there really shouldn't be much confusion between these notations. But anyway, a plus b dot x is equal to, so I can either break up the addition in the vectors, or I can break up the addition in the scalars, and it distributes it the natural way. So like a dot x plus b dot x, right? So this would be for all a and b in the reals, and for all x in the vector space. At this point, you should be dreading something like, so you're going to make me prove something's a vector space? So I have to check how many things? Oh, there's a lot of things to check here, isn't there? Yep.
Is there some way to prove like all of them in a really easy way?
I don't know. I hope so. Otherwise, it seems really mean, right? I mean, but while there is a lot to remember here, right? Everything
A lot
here
of
is
these prove each other though. Like 3 proves 4, and vice versa.
3 proves 4. Well, does it?
Does it?
I mean, so the Bourbaki will agree with you that you can reduce the number of axioms here to some more fundamental minimum. So part of the reason that I have written this many, you're right, it's for pedagogical reasons. A mathematician who was more pure of heart would reject this definition because it could be told, it could be chopped down further. But I'm going to stick with this because it's kind of the standard thing. And but you're right, to some extent. I'm not sure I can totally agree with you. The question is, what does this 0 mean? Right? I could write axiom 4, but then the question is, what do I mean by writing 0 there?
Because 0 could be a vector, or what?
What is 0? 0 is an abstract thing here. 0 is not the 0 number. 0 is the 0 vector. What does that mean for a particular context?
It could be 0 or 0, 0 or 0, 0, or what?
A set of nothing in it.
There's literally infinitely many different examples of vector spaces.
Oh, that's wait. What I'll figure it out. I'm going to class.
What I'm trying to say is, you're thinking 0 maybe from your experience, right, which is Rn, or the reals, or complexes or something, you know. But this 0 is the 0 in an abstract vector space, so it could be tons of different things. So it's a very bad notation in some sense, right, because we just use 0 for everything, but you're kind of used to this overloading of operators already in math, right? We use 0 for how many different zeros, right? Oh, what's axiom 9 and 10? That's that x plus y is a single element of V for each pair x, y, and v. I mean, so maybe I should write this first, right? And then here's another one for each. I'll write it properly here. For each c in the reals, and x in vector space, c dot x is a single vector in V. Now, I will totally agree with you, Christian, that I'm not being logically minimal here. Because since you guys, so many of you have taken Dr. Sperano's calculus, you are well aware of the definition of function, which is what? What is the critical, single, most important thing about function?
It maps
It has
to
to
a
exactly
value.
one element.
Maps to exactly one.
To a unique value.
Maps to exactly one element. That would seem to say the function's constant. I mean, hear what you're saying.
It maps to a unique element.
Maps to unique element. That would seem to me to say that.
Maps
What
to
maps to?
unique
Each-
What maps to? It's for
Each element
X
of the
element
domain
of
maps
set.
to exactly one element of the codomain.
There we go.
That's
Each. You guys, I understand. You were thinking what he said, right? But he's the one who said something about the domain, picking a point in the domain, and that point mapping to just one point, right? Each input maps to a single output. It's single valued. This is function, right? So when I write this here, plus is going from Cartesian product to that, and scalar multiplication going from this Cartesian product to that, I'm implicitly saying here that addition and scalar multiplication are single valued, right? The reason I write axiom 9 and 10 over there again is just to drive home the point. It must be that each vector addition gives you a specific vector. Each scalar multiplication gives you just one vector, okay? Yes?
That's just saying if you add two vectors, you're going to get one vector back.
Right. All right. Now we got this definition out. Does this look familiar? Can you think of any examples of vector spaces?
The Cartesian system.
Of what?
The Cartesian. Not too late.
Let's say that C sub V equals to what?
R squared.
R2? Okay, I'll take that.
Like, I mean,
With what notion of addition? What? Not a trick question.
Him. Like, he's the one who said it.
Oh, I didn't hear. I'm sorry.
I said vector addition.
Oh, it was you that
Oh.
said it.
Christian's trying to put words in your mouth.
I thought you said it. It was your voice.
No, yeah, I did say it.
Chris was using a ninja trick. He was throwing his voice into like something.
Or ventriloquist, Christian.
So yes, this paired with the usual vector addition and usual scalar multiplication forms a vector space, right? But let me take you your R2 and raise you an Rn. Okay, so if you look at this, so take x and y in Rn, then define, let's see, x plus y, we defined it as follows, right? X sub I plus y sub I, and what was our scalar multiplication? C dot x, I equals c times xi, right? Those are our definitions of vector addition and scalar multiplication for n-dimensional vectors over the reals. And in fact, if you go back in the notes, you'll see that I wrote a proposition, a seemingly boring proposition, which has all of these things. Right? I think I asked you to prove axiom 8 for Rn was one of the questions on your quiz one. Right? I had A was equal to C1, B was equal to C2, but I actually asked you to prove axiom 8 for this example on one of the quiz problems. So fundamentally, a vector space is like Rn. This is the quintessential example of a vector space, right? Now, I hope you'll forgive me if I don't show you that every one of these is true, but we actually have seen this already, these axioms play out, right? I would be bored, you would be bored. So let us agree then, it is known that Rn is a vector space going this point forward. I don't ask you to prove that. I mean, you might not, you shouldn't be bothered for me to ask you to prove that though. Asking you to prove that is a really simple question, right? If you've got 10 hours for your test. Oh, I'm starting to invite a conversation from Christian. All right, can you think of any other, what are other sets of things that we can add things together and get back the same thing? Yeah.
Matrices?
Matrices, yeah, that's a good example. So V equals to, see, basically Daniel's saying, I take your Rn and I raise you an Rm by n. I agree. That is in fact a vector space because if we take A and B as matrices, right? M by n matrices, M is in mommy, n is in nenu nenu. We can also define essentially almost by the same rules, right? A plus B ij is equal to aij. I'm going to stop writing this stuff pretty soon. Bij and c times a. The ij component of that is c times aij, right? And you know if we define a rule for a component, if we define it for all components, it suffices to define the equality of matrices. Yes, Dr. Professor Landon.
I'm not saying that, but like, what about complex numbers today or not? I don't know.
Do complex numbers form a vector space? Yes. But any questions about this? So you notice that I'm telling you now, in terms of this abstract terminology, that a vector can be what? It can be a matrix. Right? So if I want to make you think of a specific vector in Rn, I will now try to use the terminology what? I'll try to say column vector, right? Or sometimes I might say a concrete vector. I'm talking about a specific, something that could actually be viewed as a directed line segment from one point to another. You notice, I mean, is a matrix a directed line segment? Can you write a matrix as a magnitude times direction?
I mean, you can write it as a bunch of unit vectors with scalar multiples.
What do you mean? What's the length of a matrix?
Oh.
Yeah.
Would the direction be like the standard basis and then the combination of those, and then would like the magnitude?
I'm not asking. I'm not asking for any. My point is that there's no natural way to think of it.
Oh, okay.
I mean, in fact, in fairness to both of you, there actually is a way to think of it, but we'll talk about that later. But they're not vectors, right? I mean, they're not vectors in the sense we talk about them in physics or in calculus 3, right? Yeah, they're vectors in the vector space. Yeah.
Can you still do operations like you would in physics or calculus, where you say find the magnitude of one of these vectors or find the angle between?
In truth, yes, for vector spaces which permit a norm. But that's something we talk about much later. So that structure we're not touching on until much later. There is a notion of distance or length of vectors, but that's something more. What I'm trying to say is we already know a notion of distance only for Rn. That's where we have some notion of distance, angle, and stuff like that at the moment. Okay, can we add this example? What else? Any other examples? Let me put something to you that's a little bit more out there. So I will take Landon's example of complex numbers as a good example. That's essentially just R2 though. So C, basically here you have A plus IV, right? Plus C plus ID. How do you add those?
You have the real and the complex.
Yeah, exactly. So my point to you is this is essentially the same thing as this, right? But I mean, I say essentially the same, but they are different. I mean, Landon has added an example here. I'm just pointing out it's really almost the same example. Almost the same example, though, something I'd like to make more precise, and we will in due time. So yeah, complex numbers form a real vector space, right? In this way. What's scalar multiplication? Yeah. Right, it's C times this is really just CA plus I times B, not CB, right? Basically, you just proceed normally, right? Just multiply C through, that is the scalar multiplication. You could check that, in fact, it does satisfy those axioms. Now, of course, you could take me C and just as well say the same thing for what? Complex n by n matrices, right? Complex n by n matrices, I could almost I can give the same definitions as I just gave for the reals.
Wouldn't that be Cn in the third example then? Since that could be an R1, R2, R3.
I'm sorry?
Couldn't that, wouldn't the third example be
Yeah.
C to the n instead of like just C? Because it could be in any.
Oh, yeah, I mean, you could do that, but then I'm actually doing it just for complexes, but.
Fair enough. Never mind.
I mean, but my point is to use, you can, the definition I just gave for m by n real matrices, you can easily check that in fact also gives you a vector space structure for complex matrices. If you take a complex matrix and you take another complex matrix, you add them together, right? component-wise, you get another complex matrix of the same size. And you can take a complex matrix and multiply it by a real number. You'll get another complex matrix. Every complex entry multiplied by that real number, you get another complex matrix of the same size. I want to move on to more shocking examples, perhaps. How about this? What if I look at this set? How about this? ax squared plus bx plus c, such that a, b, c are real numbers.
No.
So how would you add two such things? So let's say a1x squared plus b1x plus c1, and I want to add that to a2x squared plus b2x plus c2. How would you add those? What would you make your definition of addition?
You add the terms that have the same power.
Right, so Chris is like, there's already a standard notion of adding these things. So you're just talking about quadratic polynomials, right? So you just add the coefficients, though, pragmatically speaking here, right? Is it clear that you get another object of the same type and just one of those objects? Is this a unique quadratic polynomial? In fact, it is. How would you define scalar multiplication here? What's c times, oh, my a1x squared minus b1x plus c. How would that be defined?
C a1 x squared
Right.
plus c b1 x.
Okay, let's see c1, right?
Yeah.
Is that a unique quadratic polynomial?
Yeah.
Okay. These examples are not hard, right? I'm just trying to point out to you that that has this structure. Now, you're like, so typically I call this thing P2. And sometimes, to be more specific, I might say P2 with real coefficients, right? To give you a weird example, before I give you the less weird example, you could look at P2 with, say, I don't know, 2 by 2 matrices over the reals. If you think of the A1, B1, C1, and A2, B2, C2, instead of being numbers, if you think of those as being 2 by 2 real matrices, you can see that those two definitions I gave right there, they still make sense. For example, if I had, 1, 2, 3, 4, x squared plus 5, 6, 7, 8, and well, that's not enough. I need to add that to something, right? How about 1, 0, 0, 1? Just to keep it, I'll keep it simple. I'm going to put an x squared here. So what you do is you just add this to that, keep the x squared, right? 2, 2, 3, 5, x squared plus 5, 6, 7, 8. There you go. I mean, that would be an example. But again, you could prove that polynomials with matrix coefficients had a vector space structure because you can add 2 of them to get another of the same object. And multiply it by a number, you get another same object.
Add a complex number.
Add a complex number. Probably do that too. Yes.
Is this like kind of like how when we had linear independence, you had to have additivity and like linearity, like here in order to have a subspace?
We will soon. I haven't explained what a subspace is yet, and I probably should pretty soon. Actually, let me get on with it. Is this like linear independence and spanning? I mean, those things are here to see. We will soon talk about linear independence and spanning in the abstract vector space structure, but not today. How about this? Here's a less weird example, 7. How about just polynomials?
Isn't that what you did?
That was a specific example. That was P2, but you could think about Pn being the set of possibly degenerate nth order polynomials, right? two nth order polynomials, possibly degenerate, meaning that I allow for a sub n be 0. You get back another nth order polynomial, right? Scalar multiply still. What's our definition of addition? I mean, honestly speaking, you can view number 7 as fitting inside this more general class of examples, which I usually say f.
Yes.
F, funny looking f's of R, which I'm just defining to be f functions from the reals to the reals, such that, well, f is a function, okay? This set actually forms a vector space. How?
They're just adding functions to each other or multiplying a scalar about function.
What, I mean, like I was trying to say from the start here, it's not just a set, right? It's a set paired with an addition and a scalar multiplication. So I hadn't really told you what the vector space is until I also tell you what the addition and the scalar multiplication is. For all these examples we've looked at, there's been some natural notion, some natural idea of what those operations should be, because you already have experience with these examples to some degree or another, so you already kind of have an inbred notion of how to add those, right? How do you add functions? If I have f and g in this, let me call it b, then I'll keep writing that. What do you say? How would we define f plus g? How would we define c times f?
I mean, you just add like
How do you define the new function f plus g? How is it defined? Yeah.
Like f plus g of x is equal to f of x plus g of x.
Indeed. What's this called?
Oh, that's what you mean.
And I'm asking, how do you define f plus g? I mean, that we have to show, produce some new function, and the definition is what's called by points, right? Pointwise defined. So this gives you a new function f plus g. This gives you a new function c times f, possibly distinct from the initial pair f and g, right? Does this notion of addition, does it respect those axioms? Well, if you add f plus g, is it equal to g plus f?
Yes.
Search your heart. You know it's true. If I take the scalar multiple of 1 times a function, do I get back the function again? Indeed I do. If I have 3 times a function plus 4 times a function, is it the same as 7 times a function? In fact, it is. This vector space steals all of those properties from where? From the range of the function, right? It's stealing all of those properties basically from the real number itself. Okay. So in fact, this is another example of a vector space. Here's a greedier example. Take 2 vector spaces. Actually, let me be even greedier. Let S be a set. All right? And let consider functions from a set into a vector space V, where V is a vector space. All right. So this set could be, I don't know, set of cats,
Set of functions.
lawnmowers, not ponies. I forbid that in my axioms. Moved the equestrian case.
For unicorns, not allowed either. Unicorns are under the
Unicorn is just a horned horse, so I don't know.
It could also be a
Debatable.
bull honey. And like there's very certain things that we
What about
So,
Pokemon?
so guys,
Pokemon, there we go.
So guys, how would you add things in this set? The same way as in my last example, right? You can define, how do you add 2 functions? If I get, 2 functions here, f and g from this set, then I can define f plus g of x is equal to f of x plus g of x for all x in this set S. That S doesn't have to be the real numbers. Like I said, it can be all kinds of crazy stuff. This object will inherit a vector space structure from its range. The fact that you're taking functions which map into this vector space means that these values, like f of x plus g of x, they automatically pick up all of this nice structure from the fact that the vector space itself has this nice structure in the range paired with the definition of pointwise. That is a stupidly general example. All right, so those are some of our standard examples. I'm sure I forgot something. My point to you is, let us agree that we know. I mean, I don't really want to. Not a standard example. Okay, it's a standard example, fine. Anyway, we can agree these things are all vector spaces, all right? This brings me to my definition of a subspace. What's a subspace? W, let V be a vector space. And W, a subset. Notice that this, I'm writing, it's going to be subset, so it's curly. I mean, it's not jagged here, right? That's like a C with a line under it. Subset of V is a subspace if what? If W is not empty, is a vector space with respect to the vector space structure of V. What I mean more precisely is W is a vector space in terms of the restrictions of, in terms of the operations on V restricted to W. So same addition, same scalar multiplication, but just for that subset W. Now, if this is the case, we have a really nice standard notation for this. We simply write W less than or equal to V. That's not less than or equal to. This is to be read subspace, okay?
Why don't you say the subspace? Or the subset? Or
A subset doesn't have to be a subspace. For example, great question. Let me go back over here. So yeah, it's probably helpful to see some examples of things that are subsets but not subspaces. So let's say, let's keep it somewhat concrete here for a second. Let's think about R2, all right? And I could think about W equal to, say, the set containing 1, 0. That's do you want me to make it more interesting? Fine, I'll make it more interesting. 0, 1, there. There you go. Now it's got two things. That's E1 and E2, right? Is this a subspace? Definitely a subset, right? So guys, why is that not a subspace? Yes?
You can't add two of the elements together and get another element in there.
So you're like, if I take 1, 0 plus 0, 1, I get 1, 1, right?
Yeah.
Which is not an element of W. So therefore, W is not a subspace of R2.
Oh. Because it's not a subset. Oh.
Subset is a much weaker condition. Like subspace is, it's all this.
So like it has to be inside the same set,
Yeah,
or the result has to be.
Can you guys think of anything else? There's many other axioms which are violated here, yes?
So does that mean it has to be linearly dependent?
Yeah, over the reals, if we take our field of scalars as the reals, vector spaces are by their very nature infinite. So yes, they're linearly dependent sets of vectors for sure. Yeah. What else you got here? So one of the main reasons I shared with you these axioms today, one of the main ways we use, like I told you, it's kind of a drag to prove all of these for a given example, but these aren't critical to your mission of proving something's not a subspace. If you want to prove something's not a subspace, all you got to do is show that that example fails one of these. Game over. Now, Daniel showed me that you can add them and it fails, but I would also point out there's much lower hanging fruit here. You could do this. How about this? 0, 0 is not an element of W. So therefore W is not a subspace of R2. I mean, any one, this would work, this would work. Can you think of something else? How about 2 times 1, 0 is 2, 0, which is again not an element of W because it's not closed under scalar multiplication. I think, I mean, axiom 1 is okay, axiom 2 is okay, axiom 3 fails, axiom 4 failed, axiom 5, okay, axiom 6, we're okay, that's just a generic property. In as much as, well, I think axiom 6 fails too, because of that reason. I can't make sense of axioms 6, 7, and 8 for this example, right? Because I don't have enough scale. I don't have enough vectors to even form these scalar products. All right.
But like mainly it fails axiom 9 because it like doesn't make a symbol.
Yeah. I'm a little bit short on time, so I'm going to state a theorem for you guys today, and I'm going to prove it next time. But I want to state it and use it. Here's the theorem. W is, well, again, I want to assume V is a vector space. Over the reals. I'm sorry, I did forget to put that language back in the very start. I should really say a vector space over the reals. But like I said, that's everything we're doing, so I don't, every once in a while I feel guilty for not saying it like now. Anyway, let V be a vector space. Writing, sorry. Vector space over R, and W a subset of V, then W is a subspace of V if we have the following. So 1, W non-empty. That's one thing we need. 2, if x comma y is in W, then x plus y is in W. So in other words, the space, the subspace, the proposed subspace is closed under vector addition. And 3, if x is in W, then Cx is in W for all C in the reals. All right. I'll prove that for you guys next time. I got a little bit carried away with the axioms today. Usually I just project them, but I thought, I don't know, for some reason I think it was good to talk through them today. You can prove this though. If you have these, you can get the rest from the definition, being restricting. The fact that V is a vector space allows us to prove this. So when you know this theorem, it's just amazing. Like we get all kinds of new examples of vector spaces, basically by restriction. Let me show you an example. So let's take continuous functions. Continuous functions on the reals, right? So usually we call those C0 of R. So I would argue that C0 of R is a subspace of the function space on R. So I was arguing to you earlier in this lecture that function space on R is a vector space. All right, so that's the V. And telling you that continuous functions, so how would you, okay, let's put it into action. Like, how do you prove that the continuous functions are non-empty? So how about this? F of x equals to x is continuous, right? Therefore, C0 of R is non-empty. I mean, that's kind of duh. I'm just saying, you just got to give me one example, and then that proves it's non-empty, right? And then what else do I have to prove? I have to prove that if I get 2 continuous functions, right? f and g be in C0 of R, right? Then what do I need to show? How about this? Limit as x goes to a of f plus g of x. What's that equal to? Right? But by properties of limits, what do we got? Well, you're jumping, but yeah. Property of the limits is that limits has its linearity, right? So I can limit of a sum is the sum of the limits. And then you're telling me that's f of a and g of a. Why is it f of a and g of a?
Because it's continuous.
Right. If f and g are continuous, that means that the limit of the function is the value of the function at that limit point. So that's f of a plus g of a, which, by the way, is f plus g of a. Right? So therefore, f plus g is an element of the continuous functions. So I just checked numero uno, numero dos, now 3. Almost the same argument, right? If you allow me to be lazy. Right?
So let's separate all that and during test, where we have a little bit of time.
Well, that will be one of the themes of my when you're doing this, pragmatically speaking, it's easier to check if like cx plus y is in W again. Because then if you do that for arbitrary cx and y, you can take the case y equals to 0 to get cx, and you can take the case c equals to 1 to get x plus y. So pragmatically speaking, to save yourself writing for this, it's always easier to do 2 and 3 at once by checking the cx plus y. Because if you have cx plus y, you can easily get 1 and 2 from that. So yeah, that would be useful for a test where there is apparently considerable time pressure. Yes. Can you take this example and give me 5 others? What other kinds of functions can you add together and get back the same kind of functions? Yeah.
Even functions.
Even functions, right? Oh yeah, very good, even functions. Scalar multiple of even function. Oh, that's a harder example than I was expecting. I was thinking of more low-hanging fruit, like, how about differentiable functions? Functions which have derivatives which exist everywhere. Add 2 of those together, you get another function which has derivatives which exists everywhere. Once you get 1 derivative, why not look at 2? Twice differentiable functions, 3 times differentiable functions. How about smooth functions? You take the sum of smooth functions, you get another smooth function. How about functions which have power series expansions everywhere, so-called entire functions, analytic functions? Yeah, some of those, again, entire. I mean, the list goes on and on. So once we have this subspace theorem, we can take the standard examples, especially for function space, and get tons of like sub-examples. Now next time we meet, I will tell you the even more greedy subspace theorem, and this is really, really fun. It turns out if you have a set of vectors which is formed by a span, yeah, span is coming back. I know, kind of a sore issue for some of you at the moment. But in fact, if you can write W as a span of some vectors, that proves that it's a subspace. That's by far the easiest thing. Right? Prove something is a span, you just, if you can look at it and go, oh, it's a span, then is it a subspace? Well, it's a span. So yes. That's even easier than where we're going there. Anyway, for those of you who are visiting, I'm sorry you have picked one of the more boring lectures in this semester. They're all kind of the same though. Thanks for visiting.
Fun.
Oh,
We're only
I guess I
going
haven't
to
got there yet.